Welcome to the second part of Session 5 of Operations Analysis, where we look now at special structured linear problems that are transportation and assignment models. I want to draw your attention once again to our resource allocation problem that we have considered so far, where we have, for instance, the production of different products on different resources or in different plants that are characterized by their capacity availability, and the production of the products were characterized by some kind of technology, production quote, or another kind of characteristic of that activity to produce one product of a certain resource. We have given the contribution of this activity to the overall objective that was profit maximization normally. We could also consider cost minimization. We can use the same problem structure now that we have considered so far with the resource allocation problem, and now differently interpret this resource allocation problem to a transportation problem, where we reinterpret the resources as origins and the activity that we have considered so far, the production of products, as a transportation to some destination. The origin, which was previously the resource, is characterized by an amount of supply that it can provide, and the destinations are characterized by a demand that needs to be fulfilled. So we can use the same structure and have a different problem that we can solve by the same. We can use the same tools that we have used so far for solving resource allocation problems, and we can use them to solve transportation problems. So also the simplex algorithm can be applied to solve that kind of problem. Let us consider one example. So we have here a cannery company that transports by truck canneries from origins to some destinations where we have located warehouses. At that stage, it's important to consider the characteristic of the problem. For instance, we have to match supply and demand to each other. So the demand of the warehouses need to match with the supply that is provided by the cannery origins. And we have a kind of a balanced transportation problem, but if they won't match, so if we would have a surplus at one stage or a deficit at one stage, then we need to introduce some kind of slack, or also called dummy variable, to our problem. So now what we need is we want to define the changing parameters in Excel, and we want also to make some calculation. So what we first do is we copy and paste the table of the above, our data table, and now I want to introduce some calculation. First, I want to introduce a color scheme that makes it easier to give the input data to our Excel solver. So I introduce yellow, for instance, for the changing variables, green for some calculation within Excel, and the objective function in blue. Then I know exactly where my cell calculations are located. I start with the objective now. We have to have the sum of our our transportation costs that we multiply by our changing variables. So we take some product and we multiply the transport costs by our changing variables. The sum we want to minimize. The next thing is that we want to consider if we fulfill the supply restrictions by our changing variables. For that purpose, I sum up all the transportations from Bellingham, in this case, to our warehouses, given and then summed up by this calculation. And I do the same with respect to the demand of our warehouses. So now we are all set to invoke our Excel solver. First thing, we define our objective. It is a minimization problem, and I want Excel to change the yellow cells to give us our solution. And now comes the definition of the constraints. So one constraint is that we require the supply to be equal to our input data given on the right hand side. And now I defined the demand constraint, that is our changing variables. The summation of our warehouses should be equal to our input demand given. That is all now for the constraints. I want the variable to be non-negative, and I want the simplex algorithm to solve the problem. And we found a solution. So this is how our problem looks in a network presentation. We have on the one hand our origins have a certain amount of supply, and then we have given the warehouses on the other hand with their demands given now in negative values, that together when we sum the supply and the demand up should match, so the sum would be the total sum would be 0. And we have now the arcs in between our origin nodes and our destination nodes, giving us the value of that arc. In this case, we have transportation costs. So let's consider some properties of the transportation problem. Here we consider that we have a balance problem. So we have some requirement assumptions where we assume that we live in a deterministic world. That means that we abstract from all kinds of uncertainty and stochasticity, so that each source has a fixed and known amount of supply available, and each destination has a fixed amount of demand. If these two do not match, that is given in the next assumption, then we need to introduce some dummy that takes over the slack. We have the feasibility solution property that states that our total sum of supply needs to match the total sum of demand. Only then we can find a solution to our balance problem. Then we have some assumptions regarding the costs, because we want the costs to be proportional to the amounts that are shipped, meaning that if we transport 1 unit of a certain good, that has a certain price. If we transport 2 units of that good, it has this price multiplied by 2 and so forth. So we are abstracting from every kind of discount. If we would want to include some kind of discount, then we would have nonlinearity in our objective function, and then we would leave the space of linear programming. The last property of the balanced transportation problem is that we have an integer solution. If we have the input of the supply and demand as integer values, then all our basic variables, so all our decision variables, will also have integer values. Of modeling now our problem in Empal, I'm going to open the Empal IDE, and I will now take a new file that I call transp, and I call it transportation, and I choose the file extension mod because this will be our model. Let's start with that. So the first thing, and I think it's always very handy to have the mathematical formulation in front of us, because then it's easy to translate this in Empal. So the first thing that we need to do is to define the set of origins and destinations. So I write set orig for origin, and I define it saying these are the origins. And I also give the index, because when you will deal with a lot of indices, then it is better to state them, then it's easier to track the names. And I denote it from I to M for our set of origins. And then we see that we need the set of destinations. And I do the same here, defining the index from Y1 to N. The next thing that we need is the parameters for supply and demand, starting with supply. And the supply is now over all our origins. So we are talking about the origins that have the supply. So I define our supply values over our origin set, and I require it to be larger or equal to 0. So I'm sure when there is a wrong value, then this will be catched by Empal. And I commented these are the amounts available at origins. So and the next thing we need the parameter for the demand, and the demand is over the set of destinations, and requiring this also to be larger or equal to 0, and comment amounts of demands at destinations. It is not necessary, but I introduce a check line here that checks if these two sums of supply and demand sum up. So I define sum I in origin, because this is how our supply is defined. So the sum of our supply needs to be the same as the sum of our demand, J in destination, that runs over the index J. As I said, it's not necessary, but useful. Another parameter, and the last one that is missing, is our cost parameters for transportation. So I define it parameter cost, and now our cost is defined over our sets of origin and destination. So it's a table, and I define it also larger or equal to 0. And I define it as the shipping cost. And now, we have now we have now introduced all our parameters, and now the last thing that we need is our variable. I call our decision variables trans for transportation, and it runs over the set of origins and destinations, so required to be positive. So now we have defined all our input that we need and also the decision variable for our model. So the first thing that we need to introduce is now the objective function, and then we would introduce the constraints of the model. We have a minimization problem, so we write minimize some objective that you can call as you like. I call it total cost. The name is unimportant. Important is that you recall what it is. And now the total costs are defined over all our shipping costs multiplied by our decision variable, and this summed up. So we sum over I in R origin and Y in destination, multiplied now by our decision variable trans, which was given over origin and destination, so E and Y. And we finish with a semicolon. Next thing is we need our constraints. So we write subject to. The first one is our supply requirement. So I write supply. That is done over I in origin. And we sum the values of our destinations, I and destination, Y and destination, the transportation, and this should equal the supply of our origin I. Now, if we consider once again our mathematical model, we have stated the objective function, and now we have defined the first constraint that the sum of the amounts shipped to our destinations need to be equal to the supply of the single origin. And now we want to define that the amounts shipped to from our origins need to be equal to the demand at one destination. So I write subject to demand. This is now J in destination, which is now given by the sum I in origin and our transportation decision variable over I and Y needs to match the demand of one destination. So I need a new file that I define, a data file that I call now Canary Transport. So we need to give our input parameters. This is the first one, the set of origins, and I define it together with the data of the supply that we have. So our set of origins is Bellingham. The supply of Bellingham was 75. Then we have Eugene. That is 125. And Albert. That is 100. Please recall, this is important, that you have, here we have two parameters defined. We have one defined the set of our origins together now with their supplies. So we need to have here a double point and here a double point with an equal sign. Then we can define our data and we need to finish that information with a semicolon. We do the same now for our destinations, and we already also introduce our demand, so the same as above, just for the destinations. You don't need to make tabs, but I find it useful because it gives a nicer overview. This is 65, and then we have Rapid City, which is 70, and Albert in the end with 85. Now we define the cost parameter. And now we have a table given. So we have at the first stage or in the columns we have our destinations. Here I made a mistake. Our destination is Albuquerque, for short Albuc. And now we can give the data from Bellingham. Which was 464. For Salt Lake City it's 513. And now I'm going to shorten this a little bit. So I have given now here also the cost parameters, and one might have noticed that I forgot here the double point and the equal signs to define the table. The last thing, in order to save us some writing, is that we want to give a run file, so we introduce some script. I call it transportation. That gives the commands to Empal. So the first thing is model transportation mod, and then we use the data canary transp data dat. And now this is optional. I want to use Cplex, so I say option server Cplex and the solve command. For the display of the optimal solution, I want to have a nice column list display. So I say option display in a one column list format, one column, and some value for a compound form or a more list form, and then display the command to display our decision variables that we called trans. So this is all that we needed to do. I introduced it already in the file system where we have Empal and the solvers also listed. This is important because otherwise Empal wouldn't find the files. I can see if I was successful and didn't make a mistake in saying include transportation run to invoke our script. And I made a mistake. Okay, so let's take up from here. I had just an error in my data file. So one handy thing that we can do in our data file is to define to find the data as data, and we can do so by writing data here in this case. Then we get the data in the names in blue lines. That is handy. So I had an error with some subscripts, and I just realized that here in the destination set I wrote Salt Lake in a different manner than in the cost table. So once again, let's see if I have resolved all problems now. So I say include transportation run once again. And I say include transportation run, and I have a new mistake. Yeah, so just checking once again the data file, I made several mistakes that would then Empal report me back. One was that we have parameters for our origins. The third origin is Albert, and I wrote in the cost Albuquerque. So I would have Albuquerque and Albuquerque together. That was a mistake. And I wrote in the destination file Sacramento with a K. And here I defined it with a C. So I changed this to C. Okay, I hope now we are ready to go. So I say include transportation run. And finally, I get the optimal solution that is reported as follows. Draw our attention to the next problem, which is an assignment problem. So, we basically change now our transportation problem to an assignment problem. Assignment problems are those problems where you need to assign one partner to another partner, or for instance a class to one classroom and to one teacher. So here let us consider an example. We have the company, which is a burger chain, Hot and Fresh, and they have an increase in sales volumes, and now they decide to expand their production capacities, and they want to extend it with a new wing where they will have 4 new stations to be located. So, they want to know which is the optimal location for each and every station. So which station should be located where. For that purpose, the company has given the following table with the material handling costs. And when we look at this table, we will notice one thing here. We have an M, and this M stands for a very, very big number. That is very big in relation to the other numbers that we have. So the first thing now that we could do in deciding where to put the stations, this is a very small problem, so we could say, let's go through the locations and just select the station with the minimal costs in that location. So for instance here in location A, why not allocate the drive-in? And in location B, the least costs in the column is 13, so let's position the burger station in location B, and so forth. We can do so. And if we do so, then we would achieve a total cost of 138. So the question is that our optimal solution? We don't know it just from the table. It seems to be a very good one. But can we do better? And actually we can. Go into Excel and model this problem. And now you will realize that we did not change the structure of the problem. So we still have our origins here and our destinations here. But once again, we slightly changed the interpretation of the model, leaving the structure as it is. In order to solve now for this problem, we do exactly the same as we have done for our transportation problem. So I decide that here are the changing variables, and I mark them with my usual color scheme. And the calculation now, so if the requirement of 1 is fulfilled, we calculate for each column, and we do the same for each row. Now we are still missing our objective that we mark in blue. And our objective, once again, is the sum product of our material handling costs that we want to minimize, multiplied by our decision variables. So sum product, our material handling costs, multiplied by our decision variables. So we are set now to go to the Excel solver. And here Excel has already recognized that our objective is given by the blue cell. Now we want cost minimization. We have a cost minimization problem, and our changing variables are given by the yellow cells. And now we require, first of all, our assigned stations to equal exactly the requirement 1, and the same given now for the SNGs. Next thing, we use simplex algorithm to solve this problem. And we have done everything correctly.